Awesome. Let me quickly check if I'm live and I'll wait to hear an echo. Just as a reminder, we'll be reading the Swin Transformer V1 paper today. I can hear an echo, which means things are looking good. Awesome. We can get started. And just a quick mention to everyone there, these are quite stressful times in the world. And if you are not in a position where you're in duress, please consider thinking about how you can help those uh, who are in troubled times. Thanks. With that, I'd love to get started with the paper reading group. As a reminder, I always get a few comments and I'm reading them. This is a paper reading group, it's not a paper summary group. That's why it's an hour long. But I'll always try to start with a summary. So if you're short on time, the first 5 minutes should give you the gist of what we're about to learn. But thanks again, everyone, and I'll now get started. So, as I mentioned, we're reading the Swin Transformer V1 paper today, and we won't cover V2 because I need more content for future PRG sessions. Just kidding. I think V2 of this model has some minor improvements. If you've gone through this paper, you can read them by itself, and I'll also be releasing the annotated version of this paper. So just as a reminder, last time we had read through Connext, and this is a part of the paper reading group where we've been going through a lot of papers, state of the art, impactful papers, otherwise. Here's the papers repository. I haven't pushed the annotated version of Swin Transformer to it yet, but if you just go over to this link, you can, for any future sessions, hopefully this will be on time, you can follow along any papers that we're reading. So to give you a summary of what we'll be going through, we always start with introducing the session. I just did that. I'll now quickly summarize the Swin Transformer architecture, and then we'll do an implementation walkthrough. And like always, some people do it, some people don't. I'll try to leave you with some suggested homework. So let me quickly stop sharing my screen and switch to the paper that I have just downloaded. Hopefully, the archive wasn't down today. So we're used to CNNs which follow this hierarchical learning way. And transformers follow this approach where throw attention modules at anything, you're good, right? This paper comes in the middle area where it tries to take some things from the CNN architecture and tries to apply that. What do I mean by that? So there are a few problems with the VIT architecture, and this paper came out when VIT was the state of the art. So remember, anytime we're reading a paper, it's always directed at what was happening in the world at that time in research, right? But it's been a year, and since then, this paper itself has a renewed version, and many new architectures have come out. So a few things might not be relevant here. But just to quickly summarize, on the right hand side, you can see VIT. And if you read this figure definition, I'm going to be reading through that. So Swin Transformer builds a hierarchical feature maps by merging patches. VIT, if you remember, let's see, what color am I feeling like today? Let's start with blue. So VIT actually the paper had this title, an image is worth 16 by 16. So VIT would patch your image into 16 by 16 portions. So right now what you're seeing, hopefully if you have a nice connection, is in 1080p, which means this is in 1920 by 1080. Yeah, 1920 is this. VIT would cut this into 16 by 16 pixels. So a lot of pixels and then process on top of it, right? And in essence, it would have this representation inside of the neural network as it would learn it. So Swin Transformer builds this hierarchical feature map by merging image patches in deeper layers and has a linear computation complexity. So for those of you that don't know, pardon my underlining skills. For those of you that don't know, Transformers has a quadratic complexity. Don't worry, this only comes up when you're reading papers and giving DSA interviews, which none of us like. Quadratic complexity means as you increase the number of images or the image size, the computational time increases quadratically. That's not good, right? You don't want to wait for weeks, not even days. So this has a linear computation complexity, which is awesome. With respect to input image size, and thus it serves as a good general purpose backbone. So what does a backbone mean? Let me quickly draw that. Usually whenever you're working on I don't know, a sota hot dog or not hot dog classifier, you would have this set of inputs that go through your model. Let me get rid of my headphones, and now I'll rely on the chat to make sure everyone can hear me okay, because I can't hear myself. So you have this input that goes through a model, and then you have output probabilities. But inside of this model, you usually have a defined input layer and then a certain set. This could be, a Swin transformer. So this becomes the backbone. And why do we call it a backbone? Because inside of this model, we usually chop off the head. Whenever you're doing transfer learning, let's say this was trained on ImageNet, so it would have the number of classes of ImageNet. I say that because I embarrassingly don't remember the number of classes, anyways. And let's say you're applying it to a problem that has, I don't know, 100 classes. So you'd remove the head and then add a new one that has 100 on here. A pro tip that I learned recently on Kaggle was I'll I'll mention it when I switch sharing, but you can use PyTorch lazy linear layers to not define the last linear layer dimension. I'll mention it later. But ideally, you would have to redefine this final layer. So this model that you use here, after modifying it a bit, is the backbone. This could be Swintransformer, this could be Connext, this could be VIT. If you're super rich and have more computation, I'm just kidding. It takes more to train. Connext takes a little bit less. This was just a joke. Or maybe a simpler resonate as well. So all of these models serve as the backbone. So the authors are saying because of how this model functions, and we learn about that, it has a linear complexity and serves as a good backbone for image classification and recognition tasks. Why is that important to emphasize with recognition? So I just told you that VIT works with 16 by 16 pixels, right? That is still a large number of pixels to be working with, but with segmentation, you are literally working with every single pixel, because remember, in segmentation you have to literally label every single pixel. Because of its linear complexity, Swin transformers can also be used with segmentation. And when compared with vision transformers, they produce feature maps of single low resolution and have quadratic computation complexity to input image size due to computation of self attention globally. So, VIT, we've covered this in our paper reading group. I refer you to that. But VIT has a quadratic complexity because it uses attention in every single layer. Swin transformer applies a clever approach of dealing with this. So that is the quick summary. And what makes this awesome is shifted window. So that's where the word Swin comes from, by the way. Right? That's what makes this awesome, that you first of all start with a set of patches on top of which you apply attention. So this somewhat resembles a CNN, right? Because again, you're applying some form of computation, here it being attention, to all of these layers. And using some tricks, it's been made linearly scalable. So that's the summary of this paper. And now we'll be diving into depth of how this works, what is in the paper, and we'll be reading through this. If you're going to comment that it's a long video, the first 3 minutes were for your summary. Please don't leave those comments. They make me stay up at night. I'm just I'm just having fun here. Coming back to the agenda, now I'll go about introducing and giving some more context. So hopefully more of you will stay around until the end, but we've just given the shorter summary. I've used the Swin Transformer paper. We'll be reading that. And I'll be uploading this to the papers repository soon after we end reading the paper. I'll be using the incredible Tim repository by Ross, who basically has every single computer vision model available for you. And to credit, I've also watched the video, although I don't agree with all of their channel's name wordings. But Letitia's video on Swin Transformer was absolutely incredible, and I'd encourage you to check that out. So I've learned through that, and now I'll be reteaching you what I've learned. This paper talks about the transformer takeover. So to go down the history lane, the attention is all you need paper came out in around 2017, if I remember correctly. And then you saw all of these Bert, Roberta, that's not in chronological order. I don't know, Deberta, all of these NLP models that made so huge progress, right? And then, of course, someone was at that time thinking, why not apply this to computer vision, right? I see Simply Sumant in the chat. Thanks for joining us, Simply Sumant. Is the knowledge of how transformers work necessary for this? It will help you, but you can follow along and feel free to ask any questions. I'll try to make it useful without that. So we saw this attention and transformer takeover in the NLP world. Someone was surely thinking, hey, why can't we make this work in images? So right around in 2020, you saw VIT, which was titled an images worth 16 by 16 paper. And that established transformers in the computer vision field. A few months later, we saw Swin Transformer, and as expected at that time, it would be comparing itself with VIT and showcasing how it's better than that model. So that's what the paper covers. To remind you, CNNs work like so. So you convolve over the input image and you generate this feature map. And as I had mentioned earlier, Swin Transformer are somewhat closer to this, right? So now you have this collection of transformer models, CNNs, and there's this fight going on between both of them. Swing transformer is more more on the CNN side because it's taking a few tricks from there to some extent and applying them. Last week we learned about Connext, which was a CNN that was on the side of transformers. So as you can see, this battle is getting quite interesting. This comparison is getting quite interesting. So the question I assume that are addressed in this paper is what can we learn from CNNs? Or if you read through the paper, I think Letitia mentions in her video, it's very comparable to a CNN or a unit architecture. Then the second one is how can we reduce the complexity of transformers? So how can we make VIT like models more scalable? In other words, how can we make it computationally efficient? And then what the hell does shifted window stand for? So what does Swin transformer stand for? Before we start with the paper reading, I always love to just showcase what's inside of the model. For some reason, Google Colab doesn't like me, so they always kick me off. Let's see if I can quickly print this. So what I'm trying to show you here is inside of the PyTorch implementation, what all layers exist. So instead of reading the paper, it's always a good idea to just quickly see how many conv2d layers, how many nn.linear layers exist inside of it. At least I understand better that way. So we'll quickly take a look at that. While this runs and downloads, torch.meshgrid will be required to pass indexing argument. Interesting. I've not even used that function recently, if I remember correctly. Has anyone used torch.meshgrid recently? I'm just curious about the warning. I've not seen it in a long time. So what I've done here is I first of all wrote Swintransformer here, and that of course didn't import. So then I printed out what all models are available, and you know what? Let's look at Swin Tiny Patch Windows 7. So instead of the base, let's import this one. So I've listed the models, and then I'll try to see what layers exist inside of it. So we're looking at the Swin Tiny. So the tiny version, remember with any CNN or computer vision architecture, authors always start with a smaller version and then they try to add many more layers to it to tackle more tasks. So this is a smaller version that would be less computationally expensive. So let's see. We have a patch embed layer, and inside of that we have projection and normalization. So projections are calculated by contrud three 96, so three channels, 96 kernel size of 4 by 4, stride of 4 by 4, followed by layer norms. We see a dropout of 0. That's interesting. And inside of the layers, we see the first basic layer, which has a Swin transformer block, followed by an identity and a normalization layer and a MLP. And then we have another Swin transformer block, followed by more dropout, normalization, and MLP. So let's see what's inside of the Swin transformer block. You have a layer norm, followed by window attention, inside of which you call, let's see what is being called. I believe this is attention being applied, followed by dropout, a linear layer. Again, even the dropout is being applied, it's at the value 0. I'm quite curious about that. Followed by softmax. So we learn what window attention is, but it seems like it's an attention layer that's being applied to smaller parts inside of the input or inside of the Swin transformer block. Followed by which you have a multi-layer perceptron that has simply a linear layer. Jelu, not Relu. I I'm still curious and I haven't found an answer why Jelu is being used instead of Relu. So I'd love if anyone knows the answer to that. Followed by dropout, a linear layer, and dropout again. And the same thing repeats itself. Followed by which you have a basic layer, which has again more Swin transformer blocks and more layer norm and window attention. More Swin transformer blocks, then you downsample and repeat the same. So it looks like this is being repeated a bunch of times, right? And let's see. Finally, you get to average pooling and a linear layer. So the trick I wanted to mention was PyTorch lazy layer. Sorry, it's lazy linear. Let me drop this in the chat. So the cool thing about this layer is you don't have to explicitly define, if I remember correctly, the in features. So it lazily defines the number of features required for input. And this is cool for lazy people like me. So it's an awesome trick that you all can use. Just a quick suggestion. So far we've looked at inside of the architecture and it looks like a Swin transformer block. We'll see what that is. But looks like it has some normalization, some form of attention, some dropout, and more normalization and MLP is being applied inside of it. And this is being repeated a bunch of times, and you have the classic pooling layer followed by a linear layer towards the end. So that's what is happening inside of this architecture. So again, that was from the Tim library. I installed it and imported the model from there, specifically the tiny model. Now let's jump back to the paper and I'll hide this banner. So we've looked at a summary. We've looked inside of the PyTorch implementation. Now we'll go through the paper linearly. The author's claim challenges that arise when you're trying to take transformers from language and apply them to images is that there's a large variation in how things appear, and they have a higher resolution. So again, I'll, as a reminder, how I try to read papers in this session is I've already read them, so I'll point out the important things in every single line that I think is worth noticing, and I'll go over those points. So the authors start by saying, hey, transformers work well in NLP. But you know what? Vision is more challenging. There are so many different things. Sanyam looks different one day he has a beard, one day he doesn't. Sometimes even his face ID doesn't work. No one needed to hear that. So, because of this nature of this thing, computer vision, it's a more challenging thing where you can not so easily apply attention or transformers. To address this problem, they propose a hierarchical transformer. So this is the hierarchy that they're referring to. If you look over to the right side, this particular image, this hierarchy that's being built, the shifted windows scheme brings greater efficiency by limiting self-attention computation to non-overlapping local windows. In VIT, you were applying attention to almost all of the windows. Here, you apply them to non overlapping windows. So, these windows that have been created, this window, you would have one attention being applied here and one more being applied here. Attention module. And the cool thing about this architecture is it has the flexibility to model at various scales and has a linear computational complexity. And then they talk about its performance on different benchmarks. You can read through that, but this already has been beaten, so I won't go through the individual numbers. Then in the introduction, sorry, 1 second. In the introduction, they talk about CNNs started with AlexNet and they have recently become really cool. They serve as the backbone. NLP first saw the transformers because they were really cool of modeling, really good and cool at modeling long range dependencies in the data. And this led to people thinking, hey, let's take this thing and apply it to computer vision. It's bound to work, right? And in this paper, they expand on the application such that it can serve as a general purpose backbone, as it does for NLP and CNNs. So from here, I'll skip the other parts and scroll down to the implement again. Not implementation, but the diagram where they show how this has been created. So this is the architecture of Swin Tiny, the one we looked at. Now we're looking at it in terms of visual representation. So you have, as we saw earlier, two successive Swin-transformer blocks on the right, and on the left you can see the complete architecture. So you have this image that goes through this patch partition, and we'll go back and see what that is, followed by which looks like you have stages of more patch merging. So first you partition an image, right? You take an image and cut it into smaller pieces, and then you merge them and pass them through a Swin transformer block, and you repeat this a bunch of times. If you pay close attention, you can see that the size is being reduced every time. So it started with h by 4 and w by 4. H is the height and w is the width. And now it's by 8, by 16, by 32. So it's getting smaller and smaller. And on the right, we can see two Swin transformer blocks. So reading here, MSA stands for multi-head self-attention with regular and shifted window. So it looks like inside of this Swin transformer block that occurs in every single stage, twice, sometimes six times, and most of the times twice, right? It passes through layer norm, followed by WMSA, followed by more layer norm MLP, and the same repeats. Instead, there's one minute difference that this time it's a shifted window MSA. So we looked at this inside of PyTorch, and here's how it looks visually. Again, to summarize, you have your image that somehow gets partitioned, and then you apply Swin transformer blocks. What are they? These things on the right. So some form of normalization followed by attention layers. To simply understand, you can remember it like so. And then these patches, so the partitions you created get merged somehow. We don't know how yet, but they get merged. And this repeats a few times. So this is the architecture overview. Now going back to reading in order, please let me know if this process of jumping ahead is confusing. I This is how I skimmed through the paper, so I'm just following that approach. Let's see if there's anything I want to cover here. So in figure 1a, the one we looked at, Swin transformer constructs a hierarchical representation by starting from small side patches and gradually merging neighboring patches in deeper transformer layers. That's why it's called a hierarchical representation. And using this, Swin transformer can conveniently leverage techniques for dense prediction such as FPN, unit, etc. The key design element here is its shift of the window partition between consecutive self attention layers. So as you can see, I'm looking at this figure and I'm looking at layer 1 and layer 2. This is how we start. So we create all of these patches, right? In layer L, a regular window partitioning scheme is adopted and self attention is computed within each window. So you have attention being applied to this window, then this window, and this window, right? In the next layer, the partitioning is shifted. So it's not a perfect square, it's a little shifted this time, right? So it changes a bit. And now the self attention computation crosses the boundaries of the previous windows, providing connections among them. This is quite important to understand. So in any CNN, as you go deeper, right, it starts to build a understanding of more high level features. Here, it won't be possible if you keep patching or dividing your images and keep applying attention to it. It'll just learn what's inside of that patch, right? How do you make it more global? So how do you teach your model to learn what's in the complete image, especially when you're chopping it up? So by applying the shifting, where every time inside every next layer there's a different window that's created, and then you apply attention to it, the model starts to learn features across these partitions. So this is helpful because first of all, you're still creating partitions. So it makes easier for batching and computation. But then since you're applying attention to different windows every time, your model can still continue learning about all of these features that it's supposed to understand inside of the image. This is a hot dog. This is not a hot dog. If you look closely, this is a building. This is not a building. These are trees. That's what's visible inside of this layer. This strategy is also efficient in regards to real world latency. In contrast, earlier sliding window have a higher latency. And this approach has a much lower latency. So it has higher performance compared to the others. And the shifted window approach also provides benefits to all MLP architectures. That's another claim they make. So then they talk about related works, and they mention, I believe, all of the ResNets, VGG, GoogleNet, DenseNet, HRNet, EfficientNet. I've never actually used HRNet. I'm curious if anyone has, but I've never ever come across someone who's using HRNet. I've always seen its name, but I've not used it yet. I haven't had the opportunity. Um, and then they talk about the history and general self-attention based backbone architectures, self-attention or transformers to complement CNNs, transformer based vision backbones, where they mention the VIT paper. So again, this is more of a historical catch up. If you're trying to read the paper, any paper, they always give you more context about what's happening in the general world at that time. So this is about, hey, there used to be a thing called CNNs. Those are boring now. Now we have attention. That's six here, and then we have self attention. We have self attention based backbone. We have transformers to complement. We have transformer based vision backbones. Here's the history. Here are the current models. You can read about them. And then in any paper followed by that, you usually have an architectural overview. We've already gone through this, but I'll now read through in sequential order. So we looked at the tiny version of Swin and it first splits an input RGB image into non-overlapping patches similar to VIT. Each patch is treated like a token and its feature is set as a concatenation of the raw pixel RGB values. The patch size here is 4 by 4. So we create 4 by 4 patches, and thus the feature dimension of each patch is 4 by 4 by 3. It's 3 because it's RGB. So you have 3 channels, hence 4 by 4 by 3. So you have this input image. Let's use red. So you have this input image. And now inside of it, you cut out this 4 by 4 patch. You take it out here. This would have a dimension of, see, I'm bad at counting as well. So you have this terrible 4 by 4. Let's assume this is 4 by 4, all right? So now you have this 4 by 4 patch from inside of the image, and this would have 3 channels in it because remember RGB. You create all of these patches from inside of the image, and then you have a linear embedding layer applied on this raw valued feature. Several transformer blocks with modified self-attention are applied on these patch tokens. So now you have all of these tokens, and let's say you have a lot of these, like so. So now you apply attention modules on top of them, right? To produce a hierarchical representation, the number of tokens is reduced by the patch merging layers. The first merging layer concatenates features of each group of 2 by 2 neighboring patches. So next up, as you go deeper in the model, you would have this merging layer, and now it will create smaller windows, a smaller representation. So now you'd have a larger, let's say, representation like so. This reduces the number of tokens by a multiple of 4, since it's twice downsampling of resolution. And the output dimension is set to 2C. So C is again a hyperparameter we define. If you look above, It's an arbitrary dimension that we apply. So now you have this smaller set of patches that have a hierarchy and keep getting lesser in number. And the Swin transformer blocks are applied afterwards for feature transformation. And this is denoted as stage 2. This is repeated a few times. You have stage 3, stage 4. These stages jointly produce a hierarchical representation. So you can somewhat assume that after this, you would have just one window, and this form of hierarchy is being generated where the patches keep getting smaller, and you can now represent more and more information. And some form of attention is being applied here. So, what is the attention and what is the Swin transformer block? That seems to be the secret sauce for making this work. A Swin transformer block is built by replacing standard. Oops, sorry. My hand is constantly slipping over my keyboard today. Sorry about that. Um, so, inside of a Swin transformer block, you replace the standard MSA, multi head self attention, by shifted windows. We'll just read about that here. And it consists of a shifted window based MSA followed by two layer MLP with Jelly. We've already looked at this. So let's read what a shifted window is. The problem with general self attention is it has quadratic complexity with respect to input tokens, and this makes it challenging as you go to 1080p, and then 4K becomes almost unimaginable. 8K, well, forget it. So how do you deal with this problem? So they propose to compute self attention within local windows and not globally. These windows are arranged evenly in a non overlapping manner. So these windows we looked at, these boundaries are inside of the image and they don't overlap. So this does not happen at all. So you don't have any overlapping like so, right? And let me remove the underlining because I've messed up the text. So supposing each window has m by m patches. So these patches we looked at, let's say these are m by m, and the computational complexity of global MSA and window based one can be written like so. The only thing to note here is this has a lower complexity, if I remember, compared to it. The former is quadratic and the latter is linear when m is fixed, 7 by default. So we've managed to make it more scalable by using this approach. What is the approach again? Creating non overlapping patches, merging them, the size always goes down by 4, and then applying some form of attention to this, patching it again, merging these, doing it repeatedly while keeping them non overlapping. So this shifted window partitioning in successive blocks, let's see how does it get applied in successive blocks. To introduce cross window connections while maintaining the computation, the first module uses a regular window partitioning. So the first is simply cutting into 4 or how many partitions you have. So let's say this is your original image. The first would have a regular partitioning, the first layer. Then the next module adopts a windowing configuration that is shifted. So after this, remember this still remains non-overlapping, but now you have like so. So it overlaps in the previous layer, but there's no overlap between these two blue colored patches, right? With the shifted window partitioning approach, these modules are computed like so. And if you're like me, it's a better idea to skip the math because it always confuses me. And let's take a look at this image to understand better. So you have this window partitioning, and then you have a cyclic shift that helps reduce the computational load. Then they talk about how to make efficient batch for this shifted configuration. The issue with this approach is it's not always computationally efficient. So they propose this cyclic shifting approach towards the left direction. So as you can see, there's a leftward shift every time in every layer, which the authors claim has more computational efficiency. With this cyclic shift, I don't like blue. Let's use red. I just don't like blue color. With the cyclic shift, the number of batch windows remains the same as the original regular window partitioning. And this is also efficient. Then they talk about the position bias, which I'll not cover here. It's more of a theoretical. Uh, and now you have this architecture definition. So to go back and summarize, you take the input, cut it into smaller parts which are known overlapping. Then you apply attention to it, do a cyclic shift, and apply these attention blocks again. And you keep doing it. This is more efficient than VITs. It has a linear computational efficiency and it works really well. That was a tiny version. With any architecture, you have small, base, and large. As you can expect, the number C will be increasing here. What was C? It was again this output dimension that was being set to 2C. So whenever you would apply a linear layer on the 4C dimensional concatenated features, this was making the size smaller, and that's what C refers to. So it's again a number that the authors decide, and across different variations of the architecture, it's being decided like so. C is the channel number of hidden layers in the first stage. So let me take a pause and see if there are any questions. And as a reminder, if you have any questions, now is a good time to ask them. I don't see any questions, which means either I'm, I'm doing a good job or a terrible job. Um, awesome. I'll continue nevertheless. I was just seeing to wait if any questions come in. As a reminder, I'm happy to answer any questions. I'm only recently reading these papers, so my understanding might be wrong as well. If there's anything you don't understand, please do ask. If I can't answer it right now, I'll go back, reread, and definitely answer your question again. And Sumant, I hope you didn't require the understanding of transformers so far. So, furthermore, the authors talk about their experiments on ImageNet 1K. They talk about the settings, what hyperparameters they use, how many epochs did they train for, what form of warm up did they apply. I don't think this is necessary, so I'm just glancing over the details. This is important when you're trying to replicate the paper or when you're trying to apply it to any other problem. Right now, we're just understanding how this works, and that's my goal here to tell you, hey, this is what Swintransformer is, and then you can take these ideas and apply them to your problems of interest or just try to replicate it. When you're doing that, that's when these are important. So I'm skipping again over all of these results, And the quick summary here is it also worked well on object detection. And then the authors compare it against the different architectures at that time. It also performed well on semantic segmentation. They do the minor comparisons. The reason I'm not going into these numbers is sometimes these differences are really small. As you can see, it's a 2% difference, and this paper came out in 2021, 2020, sorry, I think 2020. 2 years is a lot of time in the world of machine learning, so these numbers would have changed a lot. um I don't think there's anything else I need to compare or mention here, so I'll read the conclusion. The gist of this paper is that it produces a hierarchical feature representation and has a linear computational complexity with respect to the input image size. Swin transformer achieves SOTA at that time. I'm not sure if this is true anymore. On COCO object detection and semantic segmentation, significantly surpassing at that time the best methods. And they conclude because of this, the shifted window self attention is really effective. I believe furthermore they talk about the details of different augmentations that they had applied, the type of suppression techniques they had applied when doing object detection, or detail of every single layer. They also create a swim MLP mixer, which was quite interesting to me. So if you read the MLP mixer paper, they also try to apply swing layers there. And I believe that's all I wanted to cover here. So to summarize again, the architecture takes the image, partitions it into smaller parts that are non-overlapping, applies attention, merges them, and shifts them every time. How does it shift them? Cyclically, leftwards, and keeps applying attention. This outperforms VIT and is more scalable than that. It works better than that. At that time, it was more accurate, and it also works well across semantic segmentation and object detection tasks. So, because of the shifted window, which was key to making it work, the name Swin transformer comes from there. Awesome. Now I'll glance over any questions, and I managed to end a few minutes early, so I can always mention the homework to everyone. Someone mentioned the "you got this" emoji. I've never seen that. Thank you, Julian. Um, Again, please, if you have any questions, I'm happy to answer them right now. I'm trying to switch sharing and struggling to find the correct screen. But now let me hop over to my slides. I always try to leave a few suggestions. So I've particularly been curious what happens if you swap out GELU with ReLU. I've not found an answer yet to this. Pardon the inapt spacing there. I would invite you to try this on ImageNet. I believe that's the correct pronunciation. This is a more challenging and more accessible version of ImageNet. I would invite you to try this on active Kaggle competition. So go to any Kaggle competition, sort by best score, see if they don't use Swin transformer, try to switch the backbone. You'll get a bunch of errors. Try to get rid of the errors, try to get the model to train, and see if you can improve the accuracy. Uh, that's a lot of work, but please tell us if you try that. And I will be uploading this to the annotated paper repository, so I invite you to check it out afterwards. That's all I had for homework suggestions. I'll again wait a minute. If not, we can wrap up early today. I see a question and I'll address that. As a reminder, this is where you can find these papers. Tony, I'll just get to your comment. Can you please give some advice on how to get into a stage when reading this paper becomes more natural? You don't need to read papers. Seriously, you don't need to read papers even if you're a machine learning engineer. That's a broad statement that could get me into trouble. But what you need is the ability to iterate on ideas faster, right? And that only comes through either applying these techniques a lot and then slowly reading the paper. It's always frustrating, it's always annoying. This paper was by Microsoft Research, and is Microsoft Research's papers, apostrophe s, sorry, uh, are more accessible. So the thing to understand here is some papers are more readable than others. I have no affiliation with Microsoft, by the way. I just enjoy reading their papers. But different labs sometimes have a higher bar of accessibility to papers. Nothing against anyone. Sometimes they tend to have more jargon, so it also varies from paper to paper. I myself struggle a lot sometimes with reading papers. Honestly, there's no cheat code to it. Please keep coming to our sessions and asking me any questions. If I can't help you read papers faster, I'm doing a terrible job, and tell me, and I'll make sure you're able to read the papers faster than you were earlier. So that's the only suggestion I have. Tony mentions they saw a few Kaggle notebooks in the Pet Finder competition. That is awesome. Let's see. Let's try to find them if I can. Or that might be too slow for me right now. But Tony says that's why he's here. So hopefully, Tony, that helped you understand the architecture better. Again, what many people end up doing on Kaggle is also you see these architectures and you just swap out the backbone. Sometimes you don't even understand what's going on, and you see an improvement in accuracy. That's cool, right? Your end goal is to improve accuracy on Kaggle, and you are able to do it. But if you want to then pull back the curtains, try to understand why it works, see if you can improve it even further. We've covered this in the chai time talks. Chris Teo, the legend, Kaggle legend, spoke about this. But for that, you need to understand the architecture better. So this wasn't a comment for Tony, but it was for the previous comment. That's why reading papers is somewhat beneficial. Awesome. I hope, Tony, you found this session useful, and I hope I was able to explain Swintransformer. I'll try to find you on the leaderboard of Pet Finder. Let's see if hopefully you're on in the top 100. And I'll try to find your solution as well. But again, I'll try to wrap up here since I don't see any other questions. Thanks again, everyone, for joining. We'll meet again in 1 month. We've seen a lot of CVPR papers come in, and I'll try to read the interesting ones and annotate and upload them here. So if you're curious of any paper annotations, right now there's just one. I'll upload the Swintransformer ASAP there. Check out this repository, and you can follow along in your free time at your own pace. Thanks again for joining, and I'll see you in 1 month.